Integrated Circuit 5, Software Tools and the Methodology. IC chip, when you say chip design, there are multiple different design work required. The first kind of chip design is transistor level design, and what it is like a linear circuit, transistor and the resistor modeling. First, you have to use your particular IC fab process characteristic. You have to identify the characteristic of transistor and the resistor, and you put that in SPICE software. The SPICE software take this. Actually, transistor has many parasitic component associated with it. For example, this base resistor is a resistor associated with NPN type. This is a P, and this is the emitter N plus, and you have N type collector, and has a parasitic resistor here, and the collector embedded N plus for the collector for this bipolar. So there are many parasitic components. Those are all hammered out in the modeling, and the resistor has temperature dependency and the capacitor. Okay, and this is a transistor level design. And who does a transistor level design? The linear circuit, like operational amplifiers, the high-speed communication chip. Those are linear circuit, and that require transistor level. And transistor level, the typically SPICE software. SPICE is taking this all modeling into account and do numeric calculation. When SPICE calculate, you can calculate at the voltage domain or time domain. So what SPICE does is to linearize this all the nonlinear element. Okay, the linearize at the very small section of voltage change or time change, and it's calculated by computer the linear model. So this is amount to solving the matrix calculation, and it has a voltage and the current and time step. So each time step is calculate the voltage and current using Kirchhoff's theory. So Kirchhoff's theories is basically using a linear matrix calculation. You can solve it. You solve it at the very tiny step by step and calculate the non-linear circuit. So that's what the SPICE software is. It's very well established, and everybody use it for the design of linear circuit. Now, logic IC chip. Logic element IC chip is like you create logic element like OR or NOR or AND or NAND and flip-flop. Those elements are put in a library. and the logic designer use it. So the logic designer are given a set of library to use for designing a logic, and they don't even care how those logic elements are created. That's the transistor level circuit designer's job. They create those logic D, Q, Q bar, kind of all the element. Okay, and the memory is a special field. How to make a memory? There are static and dynamic memory. So static memory is basically latch and many latch array. Dynamic is different. This is specialized field for designing. So they are basically transistor level design with using a software tool, typically SPICE. And SPICE cannot handle too many transistors. When your LSI chip has like 1 million gates, the number of transistors could be 10 million transistor, and you cannot do this. SPICE can do only logic element or linear circuit, and remaining is just a logic design. So it's come to the second level of IC chip design. It's a logic level design, and logic library is given to the logic designer, and the logic designer uses the library to put together. And the first software tool is a logic design tool. In the computer screen, you have you place all the logic element together and connect them together and make a logic, and see if this logic operation is working or not. It's come with a logic design editor and the simulator. Simulator is you put certain logic input and output, you can get expected output or not. And this logic simulation also has often come with an optimizer, logic optimizer. Okay, but this is challenging work when it's come to the LSI. For example, there are how to make a arithmetic unit, add two 32-bit numbers, and actually there are many theory about how to do it, different way to do it. Has advantage and disadvantage. You need to understand this. Okay, and logic validity test pattern. Logic validity test pattern is something like in order to verify, see if your intended logic is working or not. For example, if it's ALU, then you add 0 1 0 1 0 1 and 1 0 1 0 1 0. See if answer will be correct. This is one case. 1 1 1 1 0. Say 1 and 1 0 0 0 0. Then it's become 0 0 0 0 0 1. So this kind of special cases, if it's working, you have to test it. So it's a handcrafted logic validity test, whether intended logic is actually realized in the design or not. So this test pattern has to be created by engineer and make sure the logic provide the function they expect to have. Okay, and now this is the validity test, and besides the validity test, we need a chip testing pattern. What is a chip testing pattern? Chip testing pattern is, for example, later you created a chip, right? And this chip does it do what intended job? For example, this validity test pattern has a limitation. You cannot test every cases, right? So if there is a one defect, one transistor is not working, it may pass entire validity test. Okay, but we cannot ship out this kind of chip, because in actual application, when you plug in CPU, then most likely it's come across very special cases that happen to use this transistor switching. Then it's fail in the field. Okay, it's a field failure. We have to avoid this. How do we test if chip made actually is exactly same as what the logic designers created? Is any defect? So this defect checking require a different set of test pattern. It's basically it doesn't make sense. It doesn't do add or anything. It's just give a random pattern to the logic, and you have registers and logic and another logic and some registers. It's complicated design, and it's almost impossible to test every cases. If there is a one defect transistor here, you may not come across with a kind of test pattern. So the test pattern, how much it can cover any defect on the logic element. Okay, so that's coverage better be like over 90%, right? And it's very hard to reach that. Even you increase the number of random test pattern and check expected output test patterns. Okay, the reason is the internal register memory element. This is very difficult to test out every case, because internal one particular flip-flop may not get 0 or 1 rarely for any cases. For example, this is an exception flag, and that kind of exception doesn't happen that often, so you may miss it, right? So what happened is this kind of chip defect test functionality test pattern. By experience, we know that you use a shift function to shift in some random data into the register. So the test pattern for the logic input, and also test pattern for the data shift into the every register element, is going to increase very well the coverage of the test defect test. Okay, this is by experience. It's very hard to theorize why that is. Long time experience tells us that that's the method we have to use. Now this logical design diagram here, we need to generate auto routing database. Auto routing, what auto routing is, the way chip is designed is going to be automatically do the placement on the chip or the gate element used in the logic design are automatically placed, and this kind of software is available. And interconnection is also done by metal, and typically you have like 4 or 5 layers of metals, and it has a hole. This is the insulator, and the insulator here. Let's say this is a emitter, and this is a metal connected like that. So this is like a PCB, same as PCB board, but for 5 layers of metal. All the component placement and auto routing. It came from PCB technology. Auto routing on a chip is made. So all the logic gates are placed, and they are interconnected by metal, and it's create a layer. This metal layer, this metal layer, metal layer 1, metal layer 2, metal layer 5, so on so. Okay, now that's the kind of process we have to go through. So logic design data file, generate automated test pattern, and also auto routing data file. So it's getting close to the completion of the chip design, but the last stage, chip placement and the power ground design. So what's happened is, when you make chip and it's all auto placed logic element and interconnected, but what is not interconnected is power plus 5 volt and the ground, and this is not done by random routing. Typically you do the macro placement, macro element. For example, this is ALU, this is static memory, and like that. And inside ALU we place ground line like a comb shape. This is the ground, and plus 5 go between comb shape, power and ground arrangement for every macro element. And the macro element is like the chunk of logic, very heavily interconnected logic. It's a cache stuff. And power consumption analysis. You have to do power consumption, how much power is consumed in each block, each macro block. And depend on the power consumption, the ground and the power metal width has to be wide enough to provide that kind of power. And that's power ground layer design. And you also has I/O circuit. So what's happened is, I/O circuit is placed, and output logic has a large transistor, provide enough fan out to go out. And I/O has typically bonding pads, and the bonding pads has a reverse diode protection for static damage, and that kind of details has to be placed. So bonding pads around, and typically those are done manually, depend on the size of the LSI chip. And another thing is auto routing, sometimes not successful. There is a lot of restriction in terms of metal width and interlayer connection window. This window and the tolerance. So often when the interconnection is too high density, it's fail. So this require a multiple times trial to see if its router can interconnect everything. So it's a challenge if it doesn't. Then you have to change the placement of logic element and redo it. So there is a try and error involved. Okay. So after all of this is done, finally chip is processed, created, and when chip is made, the functionality is verified by defect test patterns. If it's all passed, then hopefully this LSI chip is usable. Okay, so that's a quick rundown of how the entire process of designing one LSI chip. If it's not LSI chip, it's linear design is a little bit different, and high-speed communication chip will be a little bit different. Each IC chip has a different requirement for testing and the process, but overall these are the software tools and the process methodology used. Now there are interesting stuff, so-called semi-custom design. Semi-custom design is you have fixed chip design with all the transistor array and some register are already fixed location, and depend on your logic design, the logic, each logic come from the library, it's interconnected here, so you don't need a placement of a logic element. You just create logic element using this pre-placed the transistor, register, whatever necessary for making a logic. And this process is pretty automated. And after that, all the logic diagram create the auto routing, so it's all auto routed. Okay, so what's good about this is IC chip is fixed. You don't have to change, only auto routing. So the design process is fast and cheap, but the density cannot be that high. Okay, making a custom logic and placement is called macro cell method, and that's used for the custom chip design. This is not custom, this is already made, ready-made, semi-custom. And one more type of chip is like a field programmable. So it's a field programmable ROM, has a fuse, the array of hues, and you decide which one to cut on the chip to get the desired logic. And erasable is like a EEPROM. You can erase this cutting by exposing the ultraviolet light. So when the voltage, high voltage is applied, then this is not really fuse EEPROM, it's just heat change chemically to make the resistor value very high, and the same effect as fuse cut, but it's healed by the UV light, so you can erase everything and reuse it, erasable. Of course you have a limit on number of times you can erase and use it. So this kind of chip also is used often. Field programmable is convenient because when you have ROM, it's manufacturing process, the mask, one layer of the mask is programmed and used. But field programmable is you don't need any custom mask. You just put the chip in the machine and specify which one to be programmed, and you get the programmed ROM. Okay, so that's another type of IC chip. Okay, so this is a specialized field. Okay, so I think I cover most of them. So if you're interested in this, you can keep going forward to the next video.